Good day and welcome to this webinar. My name is Dwayne Mitchell and I work in MoTec's R&D Centre in Melbourne, Australia. Today's topic is what is CAN? So in this webinar we're just going to give a fairly broad brushstroke type description of how CAN works. We're not going into specific details about setup and so forth. It's more just an idea of what can be achieved with CAN. So we'll be looking at what the technical description of CAN is. We'll cover what advantages we can get from CAN. Then we'll have a quick look at wiring, and then a little bit of a detailed look at addressing and data. But we're not going to go again into specific setups, more just an overview of how CAN would work. And lastly, we're going to take a look at how our MoTec devices work with CAN and how they interact with each other, and also how they may interact with OEM systems. So CAN is an acronym which stands for Controller Area Network, and this is most easily equated to something like LAN, which is a local area network, but there are some fairly particular differences. So a controller area network is something that has what we call multi-drop capability, and that means that you can have multiple devices all communicating on the same wiring. CAN also is a very high-speed network, not as fast as contemporary LAN systems, but it's used particularly in vehicle systems, and the speed capabilities are still very adequate. So the major factor here is that with only one set of data wires, we can have multiple devices all operating at high speed. Now CAN uses differential signaling, and what this means is that we have two signal wires both carrying the same data, but actually operating in different directions in terms of how their voltages work. And what this allows us to do is have very high noise immunity, which is quite useful in a situation on a vehicle where we might be coexisting with such things as ignition systems or even CDI systems, which generate quite a lot of interference. And so the point here is that CAN is designed to eliminate those noise signals by having this differential signaling. The other thing that the CAN system does, which differentiates it from some earlier communication systems, is that CAN operates like a complete internally controlled system, and that means it packages the data that we send through, and it takes care of error checking and so forth. So as the user, we're not obliged to understand how the packaging or the error checking work. We simply tell CAN what information we'd like to transfer, and the CAN subsystem takes care of those things. Now, the other thing that CAN is very flexible about is how the data is used. And typically, the two major elements that we transfer across CAN are what we call channel values or input data. And this would be such things as throttle positions or manifold pressures, the typical hardwired inputs that you may have into an ECU. They can be transferred across the CAN bus. And the other thing we can do is transfer control data. In this case, it might be output drives, which would be controlled fans or other such things. And both types of information can coexist on the CAN bus. The other benefit that CAN bus has over earlier communication systems is that it's what we call a broadcast system. And what this means is that one transmitter can broadcast information on the CAN bus and multiple other devices can receive. So it's a lot like a cable TV system where you have many channels that you have access to, and each receiver has a choice of which channels it's going to look at. There is a difference, however, because rather than only having one device broadcasting this data, actually all devices can broadcast data and all devices can choose which data to look at. And that's where the user can determine how the data is interpreted. And in fact, the CAN bus, of course, just deals in numbers, and so the user can put any series of numbers into the CAN bus at one end, and a different device can pull it out at another end and in fact use it totally differently. Again, what the user does is just push the data in, and the CAN bus delivers it at the other device. We don't have to understand the error checking or the other subsystem technicalities. Now, CAN, due to all of these elements of flexibility, can be extremely complicated, and there are also a lot of conventions used by manufacturers and indeed by MoTec, which allow people to select defined CAN addressing and data, which we call templates. And so when you're using a MoTec device, it's quite simple, in fact, to set up communication between multiple devices, because each of those devices have a library of templates that allow you to just select what you wish to send, and then the other devices will have a similar template that allows you to bring that data in without even necessarily understanding how the formatting works. So just to reiterate what the advantages are, we can share the same sensor data between multiple controllers. So we might have, for example, a lambda channel in one device, and we can transfer that information across the CAN bus to many other devices. Another major advantage of CAN over earlier communication systems is that each item of data that we wish to transfer can have its priority defined, and also how fast that data is updated. So we can run multiple transmit speeds, and we can run multiple priorities within the CAN system, and both of these things are very easy to configure. Thirdly, we can also, devices can always decide which data they select from the CAN bus. It's not essential that they take all of the data. They can just pick and choose the things that are relevant to each device. And the benefit here, of course, is that rather than having many hardwired sensors, we can wire each sensor into an ECU or another device, and then we can exchange the data just with the simple CAN bus wiring. And in that sense, we can also add extra devices very easily. The CAN line is expandable, and therefore by just simply tapping into that CAN line, you can add a whole new device with different capabilities, and you now have access to all of the existing data that's on that data bus. Just again, we want to reiterate that the CAN system does the packaging and the error checking, so we really only have to pay attention at the, if you like, at the user level, not at the sort of the machine level. Now, just one other distinction that makes CAN a far more powerful system than previous communication systems. You may be familiar with RS-232, which is a very common serial communication system that predates CAN by many years. Now, RS-232 is not a multi-drop system, and what that means is that there's a specific transmitter and there's a specific receiver, and that's what we call a point-to-point system. So, for example, if we need to connect multiple devices together to one ECU, we would need a separate RS-232 port for each of those devices. And you may recall PCs, perhaps in the last 10 years, not so, but prior to that, many PCs had multiple RS-232 ports because each individual device needed its own port. So CAN doesn't have that restriction. We can have many devices hanging across the same data line. There are a few disadvantages with CAN systems, but in many senses that the advantages far outweigh the disadvantages. One problem is that if the bus does fail, this exchange of data, of course, won't take place. And many modern vehicles have a very high dependency on CAN bus. Typically, modern cars have ABS, gearbox, ECU. All these systems are built into the CAN bus. And if for some reason that bus fails, then the exchange of data between the ECU and the ABS system, for example, can't take place, and the vehicle is effectively useless. So it's highly critical that the CAN bus is functional, but again, it has its own error correcting strategies. So it's a disadvantage, but in practical terms, it's something that we rarely see. The other difficulty with CAN bus is that because it's in a sense a hidden system, you only see the data as it's delivered to you. You can't see the underlying error correction and so forth. If there are difficulties, it's quite complicated to find errors or faults. And in fact, we here have some very complicated analysis tools, mostly which are not within the scope of our customers because they cost $10,000 and they have they're all about critical timing and so forth. So that can be an issue. Again, however, the advantages are major, and these disadvantages can usually be dealt with fairly easily. Okay, so CAN wiring is a very simple system. It consists of two wires only. As we mentioned, it's a differential wiring system, which means that we have two voltage levels, one on each wire, and each time we have a data transition, those voltage levels go in the opposite direction. Now, this is, again, something we don't have to really concern ourselves with, but what it does do is give us very high noise immunity. Because data travels at a very high speed, we have to treat this CAN data line the same way you would as an Ethernet cable, which is why all of the CAN lines should be twisted. And in addition, to get high-speed communications, we need what we call a terminating resistor, which is a means of getting the correct signal levels across the entire CAN bus. So again, we don't wish to explain what the technicalities are here, but it's essential that if you have a CAN bus longer than really only 500 millimeters, you should have terminating resistors at both ends of the CAN bus. Now, some devices, especially OEM devices, have these terminating resistors internally connected. However, MoTec devices do not have terminating resistors. So if you want to connect multiple MoTec devices on a CAN bus, you very much need the terminating resistors. And that's really all there is to it. Because it's just a data system, we can use very lightweight wiring, and we don't need any particular current carrying capabilities. The other thing we can do, which is quite convenient, is to have a 4-wire bus, which includes 2 CAN lines and 2 power lines, which of course would be a heavier gauge of wire. And because many systems use CAN as a control mechanism, for example, headlights and fans, they can just have a high current power supply and a CAN line, and that's all they need to be controlled. So that would be the other option. In some systems we may have just a 4-wire system, and this enables us to decentralize the wiring, whereby all of the complex wiring is at the location of the device, and essentially between the devices all we have is a CAN and a power system. Okay, so now here we have an example of how these wiring benefits are used in practice. So what I'm looking at is the top 2 lines represent our CAN bus, and then I have 4 devices. Each of these are MoTec devices, and each of these devices has sensors that are hardwired into that device. So on the left we have an M800 ECU, which of course is designed to run an engine, so typically would have reference and sync inputs for crankshaft and camshaft position, engine temp, air temp, manifold pressure, throttle position, barometric pressure, all of the typical inputs you may have to run an engine. Now, some of this data can be useful for other devices, and in particular, the second device we have, which is a dash, and of course these are designed to both display information and to log information, and so we can transfer all of this engine data to the dashboard just by using the CAN line. Now, the dash itself may have something like a traction control knob, which is a 9-position knob, which is essentially just a control device that is transmitted to the ECU, and the ECU uses that to determine how much traction control is being applied. So in this case, the dash itself has no traction control capability. It's simply using the CAN bus to transfer that information from one device to another. Of course, a diff controller or a gearbox controller or an ABS controller would have wheel speed sensors. In particular, ABS controllers have usually 4 wheel speed sensors, and this information is very useful to both a dashboard and to an ECU. However, you wouldn't wire additional wheel speed sensors and then hardwire them across to each of these devices. You simply wire them to the most relevant controller, which would be the ABS or the diff controller, and then you transmit this information to the ECU and the dashboard via the CAN bus. And the last example I have here is simply what we call a dual lambda to CAN device, and that allows us to hardwire lambda sensors wherever they may be on the vehicle, and then transfer all of that information to the ECU via the CAN bus. So in this case, there's no use in the device itself. It is simply a converter that allows us to take sensors and deliver them on the CAN bus to other devices. So all of the asterisks show sensors that could quite easily be used by multiple devices. In addition, some of those are sensor channels and some of those are control channels, like our traction control knob. Now, this is another example of something we're working on at the moment, where we've actually added some functionality into an existing system. What we have is a snowmobile that has an up-down switch on its handlebar, which controls heated hand grips, which appear to be essential on a snowmobile. And the ECU in this case is not making the control decisions about how to operate the grips. The decision is actually being made by the KTC device. Now, this is a device that converts CAN information into K-line information, which is a common data standard used on many OEM dashboards. So we've actually doubled this function up. We have the switches hardwired into the ECU, and then the ECU generates a CAN message to say whether these switches are being pressed or not. The K-line converter has an internal counter which allows us to set one of 8 heater settings from 0 to 8, and then it transmits that heater setting to the dashboard, and you can see on the right hand side we have an LCD display that shows the heater setting, but it also transmits a control signal back to the ECU which actually operates the hand grips. So in this case the ECU is not controlling these things directly. It's being controlled by passing a message to the KTC, and then it's receiving a message back from the KTC which then turns the grips on or off in a varying at a varying rate to give us different heat sensing, different heat settings. So this is just an example of using the CAN line as a control mechanism, which in fact allows you to decentralize decision making as well. Okay, so now we're going to look at how the CAN system decides which data goes where. Now there are two principal elements that we need to look at, and that's the addressing and the data. So the question is, how do we define what data we're looking at? And the simple answer is that the address itself identifies the data. So it's just like cable TV channels. If you're looking for a particular thing like a sport channel, then you know which channel number to look at. There are two addressing options, 11-bit or 29-bit. Now, 11-bit gives you many addresses, in fact 2047, and 29-bit has more than 500 million addresses. Effectively, these systems can actually operate at the same time on the same bus, and largely MoTec systems use 11-bit addressing. You still have an incredibly large range of channels there with 2,000 channels. Now, again, the addressing allows us to define both what the data is going to be, and it also allows us to control the priority. A typical example of this would be an ABS system, where we may wish to transfer wheel speed data between the ABS, the ECU, and the gearbox, and wheel speed data is highly critical. And so for this reason, we use low addresses for things like wheel speed data. What happens on the CAN bus is that the low addresses always take priority over high addresses. So if we have a number of devices all attempting to transmit data at the same time, the CAN bus itself, the subsystem if you like, allows the low addresses to have the bus and the high addresses have to wait. And so this is in a sense, it's a self-controlled mechanism, and as the user, all we need to do is define what address we're going to use, and then it will be slotted in terms of priority with the other data that's being shifted on the CAN bus. So it's a very powerful system, and it's also extremely easy to set up. Addresses normally are numbered between, as we say, the 11-bit one has 2047 available addresses, and those addresses, in other words, would be just from 0 to 2047. Many devices also use hexadecimal numbering, and that is a different numeric system which is used frequently in computers. We're not going to explain what the difference is, but let's just say that decimal numbering is the sort of numbering we use from day to day, and hexadecimal effectively is a way of compacting a larger number into a smaller number of characters, and it is, again, it's very commonly used in computers. Some MoTec devices use hexadecimal numbering and some use decimal, and many OEM devices are the same. What you have to remember here is that the number itself is exactly the same number. It's simply being represented in two different ways. Now, we're not going to explain how you make this conversion. The simplest way is to simply use the Windows calculator, which you'll find on any PC. If you have a look at our display, we've got the number 1520 as our address in the calculator on the left-hand side, and that's being displayed as a decimal number. And all we need to do in the Windows calculator is enter that number and then click on the hex button, the radio button that says hex, and on the right-hand side you can then see that will be displayed as 5F0. The normal way we talk hex numbers is to say hexadecimal 5F0, for example. If you start the Windows calculator and you can't see this view, which includes the hex and the decimal button, just simply click on the menu bar that says view and you switch to the scientific view from the standard view, and you'll get these things up very easily. Okay, now the other, of course, the other thing that is critical is the data. Now, I've just shown you at the top of our screen, we have a complete diagram of what the CAN message is comprised of, and you can see there that there's a great deal of housekeeping type information that's used by the CAN subsystem. Now, we aren't that particularly concerned with the housekeeping information. It's about error correction and bus arbitration and a few other things. Effectively, the only two things we need to concern ourselves with are the message address, which is the first part, which is labeled there as the arbitration field, and secondly, the data. Now, what we're seeing there is a message address which may be either 11 bits or 29 bits. And again, we can use these things either way, it doesn't really matter. And then we have 8 bytes of data. Now, what you can see there is actually a set of data. It can be anything from 0 to 8 bytes. And so normally we refer to data, but what we refer to is a data set, because you can have multiple channels, for example, all in the same CAN message. Now, the data has to be defined in terms of where it sits in the message, and we call that the offset. So we have an offset of 0 to 7, and we can use up to 8 bytes of data. Now, that's the only time we really need to look at what the CAN message actually looks like on the bus, because again, the subsystem is going to take care of all housekeeping, and all we need to concern ourselves with is the message address and the data. Okay, so we have 8 bytes of data, and we can use this in a number of different ways, depending on, firstly, how complicated our data is, and secondly, how much traffic we have on the CAN bus. So the simplest way is to use, in one message, we may use 8 individual channels, if you like, of 1 byte each. Now, data bytes have a range of 0 to 255, and in some cases, this may not be enough to accurately represent the information we need. So, for example, things like throttle position can be reasonably well represented by 1 byte. However, there are other things that may not be. So in this example, we have a message which is 1520, and we have 8 individual data channels, and they might be, for example, engine temperature, throttle position, etc. A number of different fairly basic items of data. What frequently happens, however, is that we need more accuracy, or if you like, more resolution, and that's the next option we have is to use 2 bytes of data for each channel. And this is the way we most commonly do it in MoTec devices. Virtually all of our CAN systems work on the assumption that data is going to take 2 bytes to carry 1 channel of information. So here again we have message number 1542, and now we are carrying 4 channels of information across those 8 bytes of data, and we therefore have much higher accuracy, if you like, and we can therefore have better resolution in our data. So that's something you'll see over and over and over with a MoTec system. Now, if we want to carry more than 4 channels of data, which is frequently the case, one of the simplest ways to do this is to simply use subsequent message addresses to carry further data, and we call this sequential messaging. So in this case, message 1542 carries channels 1, 2, 3, and 4, and then we use message 1543 to carry another 4 channels of data. And when you're using MoTec devices, you can set up data sets very quickly, and by selecting a sequential mode, the ECU, for example, will automatically generate all of these message addresses. The other way we can add extra data, there are some situations where we don't wish to have subsequent message addresses occupied. So the other way we can do it is by splitting the message. This is what we call compound data. Now in this case, we actually take up the first pair of data bytes to do indexing, which is like a subheader that allows us to split the same message address into multiple sub messages. So we have a message 1542, and then the first line shows us index 0, and then we have 3 channels of data because we only have 3 pairs of data bytes remaining. In our second line, we have the same message address, but we have a different index value, and that tells the receiving device that we're now looking at channels 4, 5, and 6. So this compound data structure can actually have very long messages. You can carry up to, effectively, you can have 32,000 index values So you can carry, for example, text strings, which is frequently done on a lot of OEM systems. And therefore you will have a message identifier, which, for example, tells you the VIN number of the message, and then you'll have a series of indexed values which give you the message in hexadecimal, usually text. So that's what we call compound data. Now again, we're not going to go into a lot of detail about how to set this up. We just want to show you what the various options and capabilities are and the way that MoTec is used to, our MoTec devices are used to transfer data. Okay, so now we're going to have a look at how MoTec devices interact on the CAN bus. Firstly, we'd look at our ECUs, the 100 series ECUs, which means the M400, the M600, and the M800. And now our M84 as well, our new lower cost device, which has some CAN capabilities but is not as flexible as our 100 series ECUs. Now these 100 series ECUs are quite flexible, and indeed they also have a lot of information that's been predefined so that the customer can set them up without a great deal of difficulty. So what we're looking at here is the setup screen on an M800, and we can have 6 different CAN messages being transmitted or received, and what we're looking here is just the setup screen for the first one. So on the right hand side you can see some of our predefined templates that come from our library, and there's also some custom data sets where we can either have sequential or compound, which relates to what described in the different ways of transmitting the data. So an M800 has a great deal of flexibility. There are some limitations, but we can certainly shift data very efficiently using an M800. Now, when you wish to use an M800 with other devices, there is a numbering dichotomy between some of our devices. M800s use the decimal numbering system for CAN addresses. And so what we've got here is the help screen in the M800 ECU, and it shows you some of the common MoTec devices and then what the decimal address is and what the hexadecimal address is. You can find this in your ECU manager when you're in the CAN menu. So you don't even need to use the Windows calculator in this case, because the most commonly used MoTec devices are all listed here. Now the other most common device that MoTec uses with CAN is of course our dash loggers. Now these of course come in varying models, and some of them have more capabilities than the others, but the ADL and SDL loggers have somewhere between 6 and 32 CAN addresses. ADL2s, for example, have 32 CAN addresses, which means you can set up 32 addresses, and each of those addresses can have either compound or sequential or single type information, so that the total amount of data you can transfer is quite substantial. Now, dash loggers are far more flexible than ECUs. We have both our our templates, but we also have the ability to customize the data transmission and reception. Once again, I'm not going to describe how to do that in this case, but what we can see here is the setup for an ADL2, and in this case we're looking at a number of OEM data templates coming from Ducati motorcycles, and each of these is available as a template that we load in, and then on the right hand side we can see which channels can be picked, if you like, out of that message address. So the ADL, when we're using predefined templates, will allow us to just switch different channels on and off very quickly. These of course can be saved as templates as well and transferred to other people. Now this second screen is just showing us a little bit more detail about how the ADL CAN can be set up. Once again, we're not going to describe that in detail, but if you look at the left-hand screen, we can't see it with great detail here, but what it's allowing us to do is select what the CAN address is, what the transmission rate is, what sort of message we're looking at. And the right-hand side is a second part of this screen, which allows us to select whether it's a single type message or a compound type message, and this is where we are allowed to enter in our indexing values and to also associate each of these with the data. So this is a fairly complicated setup screen, and again, if you use the templates that we supply, you won't actually need to pay much attention to this because it's all predefined. But what it does mean is with a MoTec dash, you can certainly interact with virtually any other device that's out there. They're extremely flexible. All right, now we're just going to take a quick look at how we see CAN applications. Of course, I've shown you some earlier, but again, we have two basic differentiations. One of them is where we have a vehicle, for example, a race car, that has basically MoTec devices on it. So our first example is simply an ECU, a dashboard, power control module or a power distribution module, a PDM, and a lambda to CAN device. So in this case, each of these ECUs, as we showed earlier, has hardwired sensors going into it and then is exchanging information across the CAN bus. Each of these devices has a predefined template or library, which is available when you install the software. So to set up communications between these four devices is extremely fast. Effectively, you don't need to understand the underlying information. You can simply select the template. We also, of course, use our ECUs and our dashes in particular on a lot of OEM installations, and we also make OEM kits. In this case, we need to interact with the existing CAN systems on these devices, and typically they may have things like an ABS system or gearbox systems. There are many others as well, including dashboards and controllers and things like that. Now, the difference here is that it's not always possible to know what CAN data is required for OEM systems. We here at the MoTec Research Centre in Melbourne do a lot of research into this, and so we're constantly looking at OEM installations using our more sophisticated CAN test devices so that we can sniff out what data we're interested in, and that's how we produce the templates that are available to the customer. So what we're looking at here is an ECU and a dash with a couple of other vehicle systems. Now this is typical, of course, of a OEM vehicle where we wish to increase engine performance. So the first thing we do is replace the OEM ECU with a MoTec ECU and thus get ourselves tunability. And in this case, it's often basically essential to be able to interact with the stock gearbox controllers and such. So that's a pretty straightforward look at an application. We are planning to do further webinars, of course, and we're going to cover this in great detail, so don't be concerned about that. Now, lastly, we're just going to quickly look at how our MoTec controllers are connected to a PC. We have a number of interface devices that go between a PC and our ECUs and so forth. The CAN cable and the UTC are the ones most commonly used. Now, we have to point out that they're not a CAN diagnostic tool. What they are is a communications tool that allows the PC to talk to the ECU dash, for example. Again, if you have more complicated CAN requirements, you can't use that the UTC and the CAN cable to examine CAN data off existing systems. It's more the case that you have to give that to us or let us investigate it, and then we can supply you with information. So our CAN cable and our UTC device are simply a means of us communicating with our own devices. They're not a general purpose tool. Okay, so that's just a quick look at the two devices we normally use. You'll see that the one on the left, which we call a CAN cable, uses a printer port, which is in fact almost redundant now on most PCs. So the device we most normally would use was the one on the right, which is called a UTC, which is a USB to CAN converter. Now, most of our MoTec controllers or devices will communicate via either of these cables. However, some of our later products will only communicate with the UTC. So most of our ECUs and dashboards can be used with either type of cable. Normally on the vehicle, what we have is a 5-pin plug. These are called XL connectors or Canon connectors. And so our UTC has that as a 5-pin male plug there. And then on the vehicle, we have a 5-pin female, which allows us to connect either type of CAN cable into a PC. Okay, so that's all we're going to cover today. We have a great deal of information that, of course, we want to get across, and we have many future webinars planned. What we're going to cover in these webinars is firstly how our 2 bytes of data can be used to give varying amounts of resolution and detail, which is what we call data scaling. CAN is also used in OBD2 systems, and so many cars already have an OBD2 port, and we can actually interface our dashboards with those ports. We already have libraries and so forth which allow us to just plug straight in with a normal ADL dash and read engine data instantly off the OBD2 connector. There are a number of other CAN modes apart from the broadcast mode that we've discussed. The other one is called polling, and I'm not going to go into that today. Again, I've mentioned that there are software analysis tools, and we're in the process of developing some simple analysis tools that we can allow our customers to use to collect information from unknown vehicles, and we'll be offering that as a service which will help us to get OEM information as well. We're also going to look at integrating MoTec and OEM devices. I have shown you one or two examples of that, for example, with a snowmobile, but this is a fairly complex thing as well. Finally, there are some very complicated data structures that we haven't covered here, and many of the, for example, BMW CAN systems use extremely complicated error checking, which is required to allow the system to work properly, and we do a lot of development work on those types of systems. Finally, we do have a document which you can download, which I am now going to put up. It's going to take me a second because I can't. Here it is. Forgive me, I can't find it. Oh, here it is. Okay. Now this is a document that's been written by one of our development engineers here, and it's not a massive document, but it covers the things we've covered today in a little bit more detail. So all you need to do to download that document is click on the button that says Save to My Computer, and we're going to leave this up for the next perhaps half an hour. If necessary, you can also email us and ask for that document. So that's going to cover what we've discussed today, but it also has a little bit more detail, and you might find that's a very useful piece of information to follow on with. Also, of course, you can look at our webinars. You can download these webinars, and secondly, you can look on